Okay, so welcome to the afternoon session. Let's start. I'm pleased to introduce Paolo Villoresi from Padova University, and he will talk about advancements in experimental quantum communications. Please, Paolo.
Thank you, Limas, for the introduction. And thank you, really, thank you, sincerely, thank you for the invitation. Very pleased to be here. And admire your environment and the CLIP initiative. So the talk here is about essentially a review on current topic and results in quantum communication. The purpose is to show a number of them without going into much of a detail. Okay, the plastic. And the purpose is to essentially have some pointers. So you're welcome to come back to me on this even after the meeting, or I'll be here until tomorrow. And the idea is to present a view and a bit of the perspectives. So I'm from Padua, where there is a Center for Quantum Technologies, which is based on 4 departments to share synergies and expertise from chemistry, mathematics, physics, and information engineering departments. The rule of the game is that the time is not started, but okay. 39. Yeah, okay. No, it's fantastic. The idea is for any project that is based on the center, which counts about 50 faculty heads of all the departments, to share at least a substantial part, at least on 2 different departments, okay, in order to have very, in the reality, complementary expertise. So the idea is to have an overview on quantum communication, the tools, that is, of course, based on the fact that you have to encode, okay, quantum states in some physical degree of freedom. That, in the case of communication, is, of course, related to light, okay? Of course, we know several, say, polarization, temporal modes, spatial modes, okay? I prepared a table to summarize a bit, say, the type of environment in which you are looking for the share of quantum states, okay, and the modality. So how you encode if you are using single photon properties, so including discrete variables, or on multi-photon states, so like a continuous variable, or the combination of these things. And well, the table is for reference, putting also a few names of the group that started the demonstration. I'll focus on a number of examples, not all, of course. And of course, now we start having the lag. Okay, the first one was on the Chinese, but we all know about the Chinese, so we skip. So I would say the polarization degree of freedom, the first degree of freedom I would like to speak, is indeed the most intuitive and also very well known, has been used for the Chinese satellite demonstration, both on the space and on the ground, which was the previous slide. It was the case of our first, say, communication in space. That was one of the highlights of the American Physical Society in 2015. Is based on several others linked, including this is the in slow motion the wavefront disruption that you have after the 143-kilometer link at the Canary Islands, and is also used in the latest satellite from the Chinese Academy of Science. Well, what it shows is that I need the next. Okay. What it shows is that there's a degree of freedom that can travel on fiber as well. Not to forget that it started with the first demonstration in 1993 under the Geneva Lake, okay, that enjoyed the quietness of the lake bed, but then also the harnessing in the fiber. So it works in free space, it works on fiber. Here I've reported a number of demonstrations that we did much recently. For instance, in the context of the urban scenario in Padova, using the existing infrastructure and the university nodes a few years ago. Okay, for that you need to encode, and we have we heard from Alberto this morning the many qualities of the Sagnac loop. One other quality is to be essentially insensitive for generating qubit when you are splitting in the actual two direction of rotation a wave function, and you modulate the moment in which one part is under a modulator. So you have essentially only to select the time in which you modulate, and then you determine the state that you create when the two part of the wave function recombine at a node here, and then it's used. Okay, this, thanks to these properties of the Sagnac, say enjoy having the record low Q-bar level at the source, which is very important for the application as well as for the quality of the experiments. Okay, obviously, as we have heard, we don't have to rotate the Sagnac while we are doing. This is something that we care not to do. And yeah, as a qubit encoder being awarded and is on the baseline of several projects also of the space station. The first space agency. The first demonstration was in the domain of the optical C-band, okay, while it can be brought also in something that is more suitable for the silicon detector in free space. So like in the region about 800 nanometer, including the intensity modulator, also with a super low Q-bar. We would like to mention that in this particular domain, the latest Chinese satellite actually improved the rate and the Q-bar, and in their paper announcing it last year, they mentioned essentially the fact that they were using the Hypognac, our scheme, that improved the system with respect to the past encoder, which was based on eight lasers. This was also used in the testbed, the European testbed, to show the intermodal concept, which we introduced a few years ago now. That is the fact that you can propagate in free space and then in fiber, or vice versa, using the same degree of freedom without the need of doing the quantum measurements and re-encoding, which simplify the optical communication as well as made it cheaper, essentially. And so, for instance, here, the situation was realized in Vienna. You see the smiling faces of the people there, and have demonstrated also that in free space you are less sensitive to rain, which is also another issue for application that is relevant. Okay. You can enjoy the mode selection, the spatial mode selection that you have with the fiber injection, and of course doing it in parallel with the usual spectral selection and temporal selection, which you always have to put in place. You can say realize quantum communication also in daylight, even with the sun that is hitting directly the telescope, something say that people usually consider it impossible, including myself, until we tried and proved it false. It was okay. So you see the direct. Okay, the telescope is in directly sunlight. This can essentially the polarization degree of freedom is also convenient because it is easier to align the bases between Alice and Bob, and so we demonstrated this versatility, having sort of a star. So with one Bob, several helices, and for instance, we have an experiment here in which using a switch located here, you can have a free space link, then fiber, and another fiber link located in different areas in different little towns around Padova, and all at the end allowed the quantum communication essentially with a simplified network. We extended this type of study for the applications on a permanent network that we have that is called VEN-QCI, Veneto Quantum Communication Infrastructure, that is permanent, that is operative since a couple of years, being formally announced before the summer this year, connect Venice and Padova through nodes that run along the highway, includes private and public entities. So it's something that is operative and has essentially solved the practical problems. Okay. Polarization allows to essentially multiplex in lambda. For instance, we have this experiment showing that you can run, for instance, two protocols in the C band, one protocol in O band on the same fiber in parallel, no problems, including also the classical channel. And so it's quite convenient. We try to extend it toward mixed operation. So we have, for instance, here the scheme of the Sagnac open with a switch in order that it can operate as a, say, polarizer encoder, as well as an encoder for continuous variables when it is instead mounted in the symmetric configuration. And we have realized that the usual modulation that are, say, traditional for coherent states. And this allows the essentially possibility to switch where you have the optimal condition in one case or the other, depending on the type and the losses that you have. Okay. CV has been also studied theoretical at the moment as a suitable for satellite communication, even if the demonstrations so far were only from polarization degree of freedom encoders, but ideally in some cases this may be realized. Another important degree of freedom it comes from the temporal modes, in particular time beams. If you have qubits, they are well known since many years, of course. Also in this case, they were introduced with essentially an application using tangle state more than 20 years ago. Okay, in Geneva again, the way of realizing is using unbalanced Mach-Zehnder interferometers, both at the preparation and the receivers. This implies three. Close it by here. Thank you very much. And you have the three lobes at the receiver coming from the early, late, and early, late, early. That is the interfering part here. Okay. Actually, this has many, as well as many other applications were developed since then. Okay, but it was found to essentially hide a possible loophole in the sense that you may have that the violation of Bell inequalities may be hampered by this post-selection loophole if you are essentially measuring also these side lobes. And in our case, we enter in the timing domain by addressing this issue and essentially showing that if you have this Mach-Zehnder interferometer with the unbalancement at the receiver, you may solve the issue by using an active switch that is essentially balanced Mach-Zehnder with an active switch with an active phase modulator on it that allows essentially to divert the early pulse that comes from the source in the long arm and vice versa. And so we get rid of the side lobes and obtain the first loophole-free post-selection loophole-free Bell violation in the case of timing. Okay, we realized this on a Quantera project together with our colleague and friends from Sweden and Spain. And in particular, we were happy to have the gentleman that essentially envisaged this loophole in the team, Gianluca Lorso. Okay. In this case, with this Hugger configuration integrated, we got actually the single peak, and so get rid of the selection. This is now something that we have extended, this active switch, to improve the generation of state and the measurements that is now ongoing in our lab, both for qubit as well as qubits. Okay. The time being are also very intriguing for fundamental studies. We actually studied the effect of the essentially special relativity transformation when you have a source on the ground and essentially your interlocutor that is in orbit but has a say significant relative velocity that due to the satellite motion is also always changing, so has a continuously varying speed, and this introduce essentially such plot for the radial velocity, so from -4 to +4 in this case, kilometer per second, and this indeed create a condition for constructive and destructive interference for the simple reason that the satellite moves when essentially reflect the first and the second part of the wave function. Okay, so it may be in phase or anti-phase. So you have the probability that goes from 0 to 1 and vice versa. And we have shown that you can select this moment and have a constructive and diffractive and constructive and destructive interference using time being at the measurement, even along channels of 5,000 kilometers of length. Okay, so the superposition principle holds also on these distances. Okay, one point that I would like to also to stress is that you may be interested not only on essentially having a single degree of freedom, but more than one, okay, and to combine. The most natural, say, output would be to enlarge the Hilbert space, so you say, okay, I can send more quantum information with it, okay. But indeed, we have done it to obtain different purposes. For instance, in this case, we consider the 2 degree of freedom polarization and orbital angular momentum in an experiment together with our friends and colleague in Rome and Naples to obtain essentially properties of the state, which is the insensitivity of the orientation of one transmitted with respect to the other. Okay, because if one rotates, of course, the polarization. If you take a linear polarization, of course, it loses the alignment, so the QBER is up. Okay, but if you combine the state, and it's done by doing essentially mathematically these properties and combining it experimentally using a Q plate and quarter-wave plate, okay, a half-wave plate, well, you can obtain that the essentially rotation is compensated by the angle that is instead imparted in the other degree of freedom, which rotate at the same time. Okay, and the result, which has been obtained in a test bed of 300 meters in a very special location, was this essentially the QBER at the end doing demonstration in quantum communication remain constant. This is the donut after the propagation of the OM, okay, while the standard trend would essentially exceed the limit and go toward unfeasibility. So another example of combination, another chance, is with 2 different degrees of freedom, now polarization and temporal modes. Okay, this was essentially exploited for 59 to 20 minutes. Okay, we are going very bad. Okay, sorry. Yeah. Okay. we wanted to realize the Wheeler Gedanken experiment on the delayed choice. Okay, so these are the base of the wave particle duality in quantum mechanics, and essentially the recipe prescribed to be able to determine which type of measurements at the very last moment. Okay, and the type of measurement are wave-like or particle-like. Okay, so in this case we create a state in which the polarization acted as essentially the switch. Okay, and the phase, like the one that I've just described, we named the kinematic phase, was the wave-like properties to test. So essentially, by switching with a quantum random number generator, essentially in the future of the reflection of the state from the satellite, so when it's into the measurement scheme, we were able to select, thanks to the polarization that determine which path the returning state is following, the interference, so wave-like properties or the which path. Okay, again, 2 degrees of freedom on the same photon flying from the heavens. Okay, not for enlarging the Hilbert space, but to provide a function. Okay, this allows to essentially have a visibility in the single particle measurement of 95%, which lasts of only 5% to the wave domain, and instead we measure more than 40, incompatible with the view in which you can have a wave or a particle, but not together at the same time, which is the conundrum of quantum mechanics. For time being, the ultimate realization is also exploiting Sagnac again, okay, now nested with an unbalanced Mach-Zehnder interferometer. And this combination, in particular, the cancellation of the field that you have here with a suitable, say, moment in which you start your modulation, allows you to have a decoy state, time being full state preparation with record low Q-bar, and now the Q-bar is 61.4 10 to minus 5, which indeed are the record low, world record for Q-bar at the source. By using more nested Mach-Zehnder, you can have also QDIT done with the same system. We are thinking since several years now of the use of this state for addressing an experiment that is very, very challenging, that is bringing to space the the Colella-Overhausen-Werner test. It was done with a massive particle, but do it with light. And for that, we teamed up with an internal theorist that is from Australia, and modeled the scheme in which you can modulate the signal using elliptic orbits. Okay, it will take quite an effort because essentially it's going to be much, far away with respect to what we did in the 2 campaigns, 2015, 2017, and 19 to 2020, as well as where Michus has worked. Okay, so it's going to be quite a tough project to set up. Okay, on temporal resolution, well, I think I don't have time for this. Okay, just mention that you can do the conversion of this degree of freedom, for instance, to polarization, to time being, using a passive system, which is rather simple, based on PBS and a delay line, and you can then reconstruct it and doing the quantum measurement straight away. So in the case you have, say, modalities that require this, this can be quite convenient. Okay. So this for the communication itself. So you also need a random number for the protocols in quantum key distribution, for instance, and many others. We developed several schemes. Our best at the moment is the heterodyne of the quantum vacuum, and our latest result, essentially obtained with chips done in collaboration with Sant'Anna, were up to 20 gigabit per second, that essentially provide a source that, of course, need to be, say, then realized according to the needs. Okay, but is very, very, very good for the say, the application of today and the near future. 5 minutes more. So I would like to conclude by just looking a bit beyond the schemes. So I would say with these tools, okay, one can think of course, improving the applications. There are many. Europe is asking for these, Italy too, and so we shall definitely answer to this. But from the scientific point of view, one can see if one can look, for instance, at the transformation occurring in the space. So I will take the first example from a project we completed recently, thanks to a contract with the Breakthrough Initiatives, that is quantum inspired. Okay, so it's not using conjugate base. The purpose was essentially to search for alien life, not as was shown by observing from the ground, but indeed going directly. So send a probe to Alpha Centauri using a context in which you have a laser acceleration and then local observation. And we got our contract essentially to make the phone call home to tell what was seen on Alpha Centauri, which is our neighbor. Okay, so it's the first stellar system, but it's still 4.4 light years away. So like 4 times 16 meters. So the phone call is quite tough because if you look at the diffraction, okay, in the optical domain, if you take the distance, if you consider this is not to scale, okay, if you consider the distance and 1 astronomical unit, so the distance to Sun, which is under 50 kilometers, say million of kilometers, this is in the few microrad. The angle subtended by the Earth from Alpha Centauri is a fraction of a nanorad, okay? And if you consider an incredibly large telescope, but the things that is intended to be receiving, that is 1 square kilometer of combined dishes, that will be in the femtorad angle. And I appreciate that femtorad was also named by Bertold before, so it's not the only one. And so this corresponds to losses that are the order of 4.5 to 10⁻17. Okay, so it was quite scary, but you have to consider that the light is made of photons whose energy is rather small. And so we actually considered that even in our first experiment in space, so the first demonstration of an exchange of single quanta from a satellite, the total chain made up 157 decibel of losses, okay? And we had a few clicks per second at the receiver, okay, using, say, 10 milliwatt of power. So we say on the base of this, were essentially encouraged to provide a rationale for the design of this optical sail to do the phone call. And essentially this needs to be in the microrad divergent regime, which can be obtained with a coherent array of individual emitters done by grating coupler on the surface of the sail. If you want to learn more, we have also the error correction code for doing it, and it was a lot of fun, as you can imagine. Okay, going a bit so in more limited scenarios. So, for instance, our solar system. Well, there are ideas that essentially exploit this solar push instead of a laser push that is envisaged in this sun diver schema. So you have satellite that has these big hairs, and they are shooted towards the sun, and the egress direction and speed is enhanced by the essentially push of the radiation of the sun. Okay, they are intended to gain velocity that are at least an order of magnitude larger than what you can get with the chemical propulsion. So between 10 and 20 astronomical units per year, which can tackle problems that are, say, at the moment hot among the astrophysicists, like life in the moon of Saturn, like Enceladus, you can get there in a couple of years. So this will be done with a technology much more close to us than the solar sail, the Starshot sail, and they are actually looking for ideas to be mounted on the central thrust of the system. So by concluding, the space part has been done in our collaboration starting in 2003 in Terra. We started first, we acknowledged starting the first experiment together with Anton Zeilinger, his group, that ended up in 2008. The telescope is rather big. It's very, very tough. You need a lot of experience that comes from having done essentially all the errors possible before doing the right thing. Okay? And this over and over for all the experiments. This is the basic recipe. Okay? And in Padova, we have a ground station, a smaller one, active since a few years now, and waiting for the European or national satellites. We are doing, for instance, a quantum communication with urban and regional, say, sizes. Like we have an Alice on a hill nearby Padova, about 20 kilometers, and a closed loop, including fiber space, free space, and fiber back to our lab. And this is something that is quite unique as a test bed, and is used by also our other colleagues in Europe. Okay, this is a bit of the scheme and the adaptive optics technique that you have to, of course, master well, because even 20 kilometers, but horizontal link, they are quite tough to deal. Okay. There are a number of projects in Europe and in Italy. Okay, we have a spin-off that is doing the boxes for the application for this, and the conclusions are that QCOMs are the most fundamental level of communication. Okay, and they are based on degree of freedom. There are several opportunities on this. Try to summarize a few of the results from us on this, but there are much more. Definitely synergies between quantum and photonics are needed now more than ever. So with this, we like to address this call, this offer for cooperation with this community that also I thank very much for the invitation. I acknowledge the flagship project with SMP on secure quantum network. Also, I mentioned the fact that we shall have a space quantum information network workshop in Padova in May. Thank you for your attention.
I mean, question. Just following up from your results and your history using fibers for QKD. I wanted to ask you, what do you think about using monochrome fibers? What concern polarization purity and the fact that you may have also larger benefit for short time being? Do you think there is a future for that technology? I'm referring to nested anti-resonant fiber that now are becoming popular and with no losses lower than standard silicon fiber.
Yeah, they are definitely wonderful objects. Okay, not so easy available. Okay, and in particular, I can tell you not having tried. Okay, and I'm pretty sure that you can use them well. The point is, at the moment, you hardly find them as deployed system. And we do tend to essentially use the spools of fiber in the lab as just a very, very first, say, stage, because the actual reality is outside. So our aim says then, okay, if we have to do it, let's do it. Also, the turbulent thing, even if it's tough, let's do it in the real scenarios. And so I don't know how many of these are actually available for testing.
I know I tried once.
Yeah. Oh, lucky you. But yeah, we befriend with one of the master on this that is no longer responding for some economical, exactly.
Yeah, it's a PDP organization, the in
It's only good, okay? Only that it's up there. So.
Another quick question. Okay, so let's thank Paolo again. Thank you for the